the battery pack from last year, or on all these pods, is responsible for the main source of energy for the propulsion phase of the pod. Right here we have the battery pack as it is labeled, and the battery pack current is controlled to be on and off via two contactors right here. Contactors are just high voltage and high current rated electric switches, and then once both of these electric switches are engaged, the battery pack is able to provide power to the motor controller, which inverts it to three-phase to our motor, which in effect propels the pod. Both the motor controller and the pre-charge circuit right here will be covered in the high voltage system team video, covered by Wyatt. You see what we have the acronym, the BMS and IMD. That is our battery management system and our insulation monitoring device. It is a proprietary or single party device that we are able to connect the battery pack to, and this device monitors each individual cell's voltage, internal resistance, current, and make sure the pack is in a good state of charge before we are able to discharge it, along with a good state of health to accompany an appropriate state of charge. The battery management system also contains an insulation monitoring device, which is basically a device that measures the insulation between the high voltage and low voltage systems to detect any low resistance paths, basically, so there are not any shorts, which could be pretty catastrophic. We'll show you what the battery management system looks like in a following scene, but that's the basic utility of it.
And the battery management system also monitors temperature of the cells, which is very important, so we don't have thermal runaway and don't lead to failures through overheating of cells.
That's right. All right, so up here we have the shutdown circuit. The shutdown circuit is the battery's primary circuit that we make. I should say low voltage circuit that we make. It is a circuit that consists of 7 or 8, depending on which ones are populated, inputs. Basically, all these different inputs need to be in a go or okay state for this low voltage or low side contactor to be engaged. If any of those inputs to the shutdown circuit are in a fault state, this low side contactor will not be able to be engaged, and the battery pack will not have a complete circuit to the motor controller, and the battery pack will not be energized effectively.
And it's a relatively easy, simple way just to make sure everything's operating in a safe manner, because the battery pack is high voltage, high potential, and it can be dangerous if we have issues pertaining to like too much voltage or not safe operation.
Yeah, and we'll show you the shutdown circuit in a following scene.
The 300 amp fuse and the manual disconnect. The 300 amp fuse is just any other fuse. If there's 300 amps of current or more, that fuse will blow, basically opening the circuit so we won't have flow anymore. Just another safety feature. And then we also have the manual disconnect up here, which is basically just a giant box that we can pull out, and when we do that, we cut the circuit too, not allowing the current to flow.
Yeah, the manual service disconnect is a required part of every pod, and its main utility will be if these two contactors, if both of them are to fail, say, and fuse shut, and we cannot open the circuit in any other way, this will provide means to do that in a safe way. So as we mentioned, we would touch on the shutdown circuit. It may look a little confusing at first glance, but I assure you it is relatively simple and is pretty streamlined in its function. So the overall, you have a low voltage 12 volts starting up here, and it has all these inputs on this main bus right here, and all of these inputs need to be in a okay state for there to be for the 12 volts to propagate to right here. And if it is able to do that to right here, it will drive the low side contactor
shut, which allows the current to flow in the main battery system.
Right. So as for these individual inputs that go into the shutdown circuit, we have 7 here, and I guess I'll start up top here. So right up top, we have the master switch for the high voltage system. It's just a simple switch that, when on or off, will break this circuit or not, and that switch is located at the back of the pod. Next in series on the circuit is our emergency stop. This is simply just another switch that we have at the front of the pod directly in series with the circuit that, if pressed, will open the circuit and effectively open the low side contactor, turning off the battery. Next up is looks slightly more complicated, but the gist of it is this part of the circuit takes in a signal from the battery management system, and if the battery management system senses that any of the batteries are in an under voltage state or over temperature state, or we are discharging at too high of a rate, it will go to an open drain signal, which will basically open up this relay right here, effectively breaking the circuit. Also on this little part of the circuit, we have designed a latching feature that must be applied from our microcontroller, or the BeagleBone in our case. It's just called MCU latch. Basically, once the MCU or the BeagleBone sends a signal, this will close, the relays will close, and if the battery management system is in an okay state, they will remain closed. And if they are not, once the signal is unapplied, it'll open again, and the contactor will not be driven. Down here on the left, we did not use this circuit, but we had it built into the circuit just in case we wanted to use an additional feature. It's the exact same circuit as this guy up here, just another input for it. The same deal is true right here, except we did use this section of the circuit. It is the input for the insulation monitoring status off the battery management system. So the same application applies. Basically, the battery management system will provide an open drain signal or a ground signal, basically, for this relay if it is in an okay state, and this relay will be able to close once we have a signal from the microcontroller to close the relay. Next in series is an inertia switch. Again, this is just a simple on or off switch. It's just a sensor located on the pod. If the pod experiences a collision or a high rate of deceleration or acceleration, the switch will open and effectively turning off the low voltage or high voltage system. Last up is our MCU or BeagleBone enable. This is a signal straight from our onboard computers that, when enabled, will close this relay and provide the last jump to get 12 volts to the low side contactor right here.
So we're just going to explain what these optocouplers are, like these little circuits that you see or the components you see kind of scattered throughout the circuit. So what an optocoupler is, it's basically a transistor, which is basically just an on and off switch, except the optocouplers isolate the two sides of the switch. So you kind of turn that on and off separately from the other side. And you do this when you have like different voltages on each side. You don't want them interfering with each other. So like this MCU latch signal will go across here, which turns on this LED, and then the light from the LED will be transmitted across to the transistor part of the optocoupler, allowing the current to flow through. So it's just an isolated measure that we take to separate the two sides of the circuitry. Yeah, go ahead.
And all this other, all the LEDs you see here kind of take up a lot of space and look kind of complicated. Those are just indicator LEDs on our printed circuit board. So when we are bringing up this board and circuit, we can tell which of these inputs are closed and which are not, and it just kind of helps with debugging and functionality. Yeah, one more note that I'll add is these headers we see right here, located across each input of the circuit, are just for debugging purposes, or if we don't want to use a section of a circuit, we can simply jump these two sections or these two elements of the circuit, or here, or any of them, just to basically take the circuit element from that one input out of it, and just know that it'll always, the current will always be able to flow through that section of the circuit. So this is what the battery system looks like in person off of pod 4. Obviously not as clean as it looks in the block diagram. That's just the way it goes. So this main white box right here is what the batteries are housed in. They currently are not in there because the pod just got back from shipping from California and there are restrictions on how many batteries you can ship together. But basically all the batteries will be in series here. Here is the box that encloses those contactors you saw in the block diagram. And then we have the high voltage wiring, the orange stuff that gets fed into the pressure vessel, which houses the motor controller. Right there, that orange guy is our high voltage disconnect that you saw in the block diagram. The part that you take out is actually not attached right now. So that's what it looks like in the safest state. Right here, we have our battery management system. You can see we have all these wires, excuse me, from here, basically off each module of cells that is fed to the battery management system here. Each one of those, or all these wires, measure each cells in the battery's individual voltage, and then from there you can derive current, internal resistance, and then there will also be temperature sensors in here, which get fed to this thermal expansion pack, which are also routed right here to measure the temperature on the batteries. Quick on the back of the pod, there are these 3 lights. They probably will remain similar for pod 4. On the bottom here, we have this high voltage on light. That is a light that will only be on when the battery pack, or excuse me, when both of the contactors are closed and high voltage is present. There's a complete high voltage circuit present on the pod. This light is actually powered directly off the battery pack power. It's not through any other low voltage circuitry, so there can't really be any faults or any say if it was controlled through software and you have a bug in your software, or your low voltage power goes off but your high voltage is still present, this wouldn't be on then. But because it is powered straight off the battery pack, you can't have any misinterpretations like that. The other light above this is the installation monitoring device OK light. When this light is on, there is sound isolation between the high and low voltage systems. So the pod is in a safe state to approach when that is on. And then this light up top indicates that the low voltage power is on the pod. And then these 2 things that you see right here, those are inputs for the switches for the low voltage and high voltage systems respectively.